she's going to talk about Steinberg slices and group-valued moment maps. Anna, please.
Thank you. And I want to thank the organizers for the invitation to speak in the seminar, which I have been attending, I guess, for over a year now. So it's exciting to have the opportunity to give a talk. So I want to begin with the basic data of this talk. We start with the group G, and it's connected semi-simple over the complex numbers. And I require G to be of adjoint type, which means that its center is trivial. So if you want, basically for this entire talk, you can pretend that this group is PGLNC. And then I fix some data about it. So L is going to be its rank, and G tilde will be its simply connected cover, which you can imagine is SLN. And then I have a natural action of the adjoint group on the simply connected group just by conjugation. So in the simply connected group, there's a kind of open dense locus, which consists of regular elements. And these are elements whose centralizer, which I denote by CGH. So this is elements A in G with the property that A centralizes H. The centralizer has the smallest possible dimension, which is equal to the rank. So in other words, this is the locus of elements whose conjugacy classes are of maximal dimension.
Anna, sorry, just a short question. So this regular locus, is it in G tilde or in G?
It's in G tilde. So it will become clear later in the talk why this seems like a kind of contrived situation to have one adjoint group and one simply connected group, but it will turn out to be necessary.
Okay, thank you.
So I have in the regular locus a dense subset of regular semi-simple elements, and these are elements whose centralizer is maximal torus. So if you are thinking about SLN, a maximal torus is just the subgroup of invertible diagonal matrices with determinant 1. And H can also be, on the other extreme, regular unipotent. Unipotent means that when I take the adjoint matrix of H and I subtract the identity, I get something that is nilpotent. So one example of a regular unipotent element in, say, SL3 looks like this. And then the adjoint centralizer of such an element is an abelian group that is isomorphic to an affine space. So in this case, our adjoint centralizer is living in PGL3 and just looks like matrices with constant entries along each superdiagonal.
Sorry, another question, short one. Is G tilde also algebraic necessarily or not?
Yes, so we're over the complex numbers.
Okay.
So if I take the simply connected cover of an algebraic group, I get another algebraic group, and it's a finite central extension. Okay, so this is a basic setup. And then there's a famous theorem of Steinberg, which says that there is a rank dimensional cross-section to these regular conjugacy classes. So an affine space that lives inside the regular locus of G tilde that intersects every regular conjugacy class exactly once and transversally. And I won't give the definition of what the slice is in full generality, but I will give one example. In SL4, the slice consists of matrices that have arbitrary entries in the first column up until the last entry, which is a power of -1, and then ones on the first upper diagonal and zeros everywhere else. And this is, I learned in giving talks about this project that this is actually a normal form that some people encounter in linear algebra, so it's sometimes called Frobenius normal form.
Isn't this called a rational normal form?
I think sometimes it's also called rational normal, but again, I never learned this, so I only know this from like sampling other people's comments in my talks. So this first column has to do with the coefficients of the characteristic polynomial. And Steinberg's theorem says that every regular element in G tilde is conjugate to a unique matrix of this form. Okay, and then using this, we can define our main character.
Sorry, Anna, the choice. Sorry, sigma. Do you choose? It's not unique, right? Do you choose some Coxeter element or something? Or?
Exactly. So for I'll say for the experts that what you do is you make a choice of like triangular decomposition, and you fix a Weil group, and inside the Weil group, you take a Coxeter element. And then sigma is I take the maximal unipotent subgroup and I translate on the right by a representative of this Coxeter element. And then I intersect with the opposite unipotent translated on the left.
Right.
So yes.
And then, so even here, there's a choice of some torus element. So
even here,
yeah.
So I mean, everything is isomorphic, but it's not like
right. Okay.
And also, since I've said this, I will also say that I can write this as I can pull out a C. And now you can also see what I claimed about the dimension, because the dimension of this intersection is exactly the length of the Weil group element C. And if C is a Coxeter element, then this length is exactly equal to the rank. Okay, so now we define the multiplicative universal centralizer to be the set of pairs A in the adjoint group and H in the simply connected group, with the property that H is in the Steinberg cross-section and A centralizes H. So we should think of this as a family parametrized by elements of the Steinberg cross-section, and above every element is sitting its adjoint centralizer. And okay, so already I gave this definition, but obviously some of the words in the definition cannot possibly be part of a definition. So I said that this variety is smooth and symplectic, but a priori, it's not at all clear where a symplectic structure would come from. So during this talk, I want to answer 3 questions. The first question is I will explain where the symplectic structure comes from in a way that's maybe not exactly historically the way that people found the symplectic structure, but that is sort of generalizable. And then the next part of the plan is to produce a fiber-wise compactification of this universal centralizer. So to find a nice way to close the fibers to get some kind of smooth quasi-projective variety that lives over the slice sigma. And then the last question, once I have this compactification, will be if I take the symplectic structure and let it approach the boundary of the partial compactification, what happens to it? And we'll show that it extends to a log symplectic Poisson structure at the boundary. So these are the steps. And now to answer the first question, I will have a brief reminder on quasi-Poisson manifolds. I'll pause for a second if there are more questions before we keep going.
Maybe one question, how is it, how obvious should it be why it is symplectic, or is it some modular space, or what is it?
So right now it's not at all obvious that it's symplectic, okay. But it will be in a couple of slides.
Okay, thank you.
Okay, so So I fix a bit more data. So factor G is going to be the Lie algebra of our group, and this is equipped with the killing form. And because the group is semi-simple, the killing form is non-degenerate. So this gives me a canonical way to identify G with its dual G star. And then I can define a 3 form in the third wedge of G star. That is the 3 form which takes 3 elements of the Lie algebra, takes the Lie bracket of 2 of them, and then pairs with the third under the killing form. And then under the identification between G and G star, this corresponds to an invariant element of wedge cubed of G, which is called the Cartan 3 tensor. And then anytime I have, oops, no, that's good. Anytime I have a complex manifold with an action of the group G tilde, I also have an infinitesimal action map. And under this infinitesimal action map, sorry, I hope you can't hear the traffic outside my apartment. Boston drivers like to honk. So under this infinitesimal action map, our Cartan 3 tensor chi becomes a trivector field on the manifold M. And now I give the following definition, that a quasi-Poisson structure on M is a bivector field pi with the property that a Schouten bracket with itself is equal to this Cartan trivector field. So I've attributed this definition to the authors of this paper where I learned about quasi-Poisson manifolds, but there are several other papers from the same period written by subsets of these authors and also other people on adjacent topics. And this is not something that I'm an expert in. So if I've made a mistake in my attributions in this talk, I would be grateful if someone corrected me. So, so what does this definition tell us? It tells us that if I think of pi as producing a bracket on functions on M, then the Jacobiator of this bracket, instead of vanishing the way that it does for a Poisson structure, instead is a sort of canonical trivector field induced by the group action. And then I call such a manifold Hamiltonian if it comes equipped with a group valued moment map that satisfies the multiplicative analog of the usual moment map condition. And for quasi-Poisson things, we have analogs of many usual definitions. So I call this Hamiltonian quasi-Poisson manifold non-degenerate if the bundle map that takes a covector and an element of the Lie algebra to the image of the covector under pi sharp plus the vector field induced by the Lie algebra element, if this map is surjective. So you see that if my group action was trivial, then a quasi-Poisson structure would just become a Poisson structure because chi-m would vanish. And similarly here, if the group action was trivial, then this requirement would just say that pi sharp as a bundle map is surjective, and this would be the usual definition of non-degenerate Poisson or symplectic. And when this happens, the quasi-Poisson manifold has a compatible 2 form, which is called the quasi-Hamiltonian 2 form, which is in general not closed and potentially degenerate. And it has the property that its differential is the pullback through the moment map of minus the Cartan 3 form that we defined earlier. And then more generally, the image of this bundle map is a distribution in the tangent bundle. And this distribution is integrable, and it integrates to a foliation of M by non-degenerate leaves, each of which carries a quasi-Hamiltonian 2 form. So I will give a couple of examples, and I will also briefly explain another way of looking at quasi-Poisson manifolds, and then I will relate them back to the universal centralizer picture at the beginning of the talk. So our first example is just the group G acting on itself by conjugation. This has a quasi-Poisson bivector, which I've called pi CD, which stands for Cartan-Dirac. Like in some places in the literature. And here the moment map is just the identity, and the non-degenerate leaves are exactly the conjugacy classes. So we should think of this as being a multiplicative analog of the KKS structure on the Lie algebra G, or equivalently on its dual under the killing form identification. And then for experts, I want to say, because it plays a big role, not so much in the results that I will present, but in the proofs, that these quasi-Poisson structures are a particular kind of twisted Dirac structure, where the background 3 form that gives the twist is given by this negative pullback of the Cartan 3 form. And if we view them like this, then the moment map becomes a forward Dirac map between our quasi-Poisson manifold and the Dirac structure on G tilde given by the Cartan-Dirac bivector. And whenever I have a Dirac structure, I can project the Courant algebroid onto the first factor. And if I look at the image of the Lagrangian subbundle LM under this projection, it gives me a distribution NPM. And this distribution produces the presymplectic foliation, which in this case is exactly the quasi-Hamiltonian foliation that I introduced before. Okay, so second example is what I call the double. This is the product of the group G and its simply connected cover. And it has a non-degenerate quasi-Poisson structure for the two-sided action of G tilde that's given here. So if we thought of G tilde as being a multiplicative analog of the KKS Poisson structure on the Lie algebra, then we should think of this double as being a multiplicative analog of the cotangent bundle of G, which I can identify with G cross Lie algebra via left trivialization and the killing form. And just like the cotangent bundle has a symplectic, which is to say non-degenerate Poisson structure, this double has a non-degenerate quasi-Poisson structure with a moment map valued in the group that is essentially a direct multiplicative analog of the usual moment map for T star G. So I welcome questions or clarifications.
Maybe one naive question. So here, you're saying that double is a product of G and G tilde, and then just to make sure. So A is in G or H is in G? Who is in G? Who is in G tilde? Looking
So,
at yeah.
Everything is in the order in which it appears. So A is
but is it really true? Because G1, A, G2 minus 1. I mean,
so,
I think, isn't it the other way around?
no, so G tilde can always act on its adjoint form, right? Because I can just.
Oh, you say you just project.
Yes,
Okay.
you just project.
Okay.
So this is really what I've done essentially is that there's this thing called the the internal fusion double, which appears in your papers. And this is the quotient of that space by the center of the group on the left.
Okay.
And otherwise, everything is the same. So the only place where we have to be careful with the group actions is that when I want the adjoint group, like in this moment map, here the adjoint group is acting on the simply connected cover, then I always have to conjugate, because otherwise the action won't be well defined.
Okay, thank you.
And again, I promised that it would very soon become clear why I am using this definition with all the G's and G tildes and not more standard definition with just the same group everywhere. Okay, so here comes first theorem. I begin with a Hamiltonian quasi-Poisson manifold, and it has a stratification by quasi-Hamiltonian leaves and a moment map. And remember from the beginning of the talk that inside the target of the moment map is living the Steinberg cross section, which is transverse to what we now know are the quasi-Hamiltonian leaves in G tilde, which is to say the conjugacy classes. And then the statement of this theorem is that if I pull back this cross section under the moment map, I will get a smooth submanifold of M, to which I can pull back the Dirac structure on M. And when I do this, I will get something that is an honest Poisson structure on M sigma. And the symplectic leaves of this Poisson structure are going to be exactly the intersections of M sigma with the non-degenerate leaves of M. And the symplectic forms will just be the restrictions of the quasi-Hamiltonian two forms to this intersection. So I don't want to say a whole lot of detail about this, but I do want to say that there are several statements embedded in this theorem. So one is that the transversality downstairs sort of pulls back to a transversality upstairs, which makes it possible to pull back the Dirac structure LM to the slice. And the other statement that is embedded here is that generally when I pull back, I will get the restriction of this Cartan 3 form. And the implicit statement here is that this Cartan 3 form is going to vanish along M sigma, or equivalently along the Steinberg slice that lives inside G tilde.
Is it easy to see that this reform vanishes on?
It's easy to see if you write out the definition of the slice carefully and also of the 3 form, but I haven't done this here. But this is a kind of special feature of the slice.
Okay, thank you.
Okay, so let me to answer that question slightly more fully. Let me say that the reason why this happens is that you recall the 3 form was given by X, Y, and Z maps to the killing form of X with Y bracket Z. And if you sort of do everything correctly on tangent spaces, then this 3 form vanishing on sigma is equivalent to the fact that if I take the derived subgroup of the Borel, this is orthogonal to the Borel under the killing form. So this is, I don't know if this is a useful answer or not, but this is sort of meat of the computation.
So can I ask you one thing about this? Sigma itself has a Poisson structure because it's a transversal and the form vanishes on sigma, right?
Yes, it has the trivial Poisson structure.
Is it trivial? Ah, okay.
It intersects every conjugacy class in a single point. So
Right.
they're just points.
So, and it only intersects regular conjugacy classes, is it?
Yes.
Oh, I see. Okay. Thanks.
Okay, so then first application of this theorem is to the example that we had before of the double. So this is our, what do I want to say? This is our moment map to the double that takes a pair a comma h, and in the first coordinate it conjugates h by a, and in the second coordinate it just inverts h. And inside here we have a Steinberg slice, and I modify it slightly to make it sort of compatible with this map. So I is going to be just the inversion map from G tilde to G tilde. So this is pairs of one point in the slice and one point in the image of the slice under inversion. And the theorem on the previous slide tells me that if I take the pre-image of the slice under this group B moment map, I should get a Poisson manifold. So it's clear from the definition that the image of this moment map consists of pairs G and H with the property that G is conjugate to H inverse. And because the Steinberg slice has this property that it intersects every regular conjugacy class in exactly one point, the pre-image of the slice sigma cross inverse sigma is just going to be the pre-image of sigma diagonal or anti-diagonal, I should say. And you can see immediately from the definition of this moment map that if I take the fiber above the point h comma h inverse, I will get something that is exactly the centralizer of H in the adjoint group. So in other words, what have I done? I've shown that the pre-image of the Steinberg slice under this group valued moment map is exactly the universal centralizer that I defined earlier. And then theorem tells me that this implies that this universal centralizer is smooth and Poisson, and that its symplectic leaves are its intersections with the non-degenerate leaves of the ambient manifold. But then the ambient manifold in this case was a non-degenerate quasi-Poisson manifold. So this means that universal centralizer is symplectic.
I'm wondering, I probably keep asking this. I prefer to think of this DG as a kind of groupoid, like a quasi-symplectic groupoid. And I would assume that this mu inverse of sigma delta is now a subgroupoid, and so it's probably a symplectic groupoid.
So I think that this double, you can view the double as a groupoid in two ways. It's a groupoid, it's an action groupoid. So source is the group element, and then target is given by conjugation. Or you can view it as a group scheme, so just as a bundle of Lie groups over G. Mm-hmm. My understanding is that it's a quasi-Poisson groupoid in the first sense.
Right.
But for what comes in this talk, I want to think of it in the second way, as a trivial bundle of Lie groups. Mm-hmm. And then, so in this case, I think what you said is exactly true, but it won't
remain true.
What follows. Mm-hmm. So yeah.
But it's like the symplectic groupoid integrating the zero Poisson structure on sigma. Then.
Like the symplectic, yes, I believe so.
Yeah, indeed. So I was also wondering if it's related to the cotangent bundle then.
So it is, in the sense that it's I said that we should think of DG as being a kind of multiplicative analog of T star G. And then DG is exactly the groupoid integrating T star G. But again, this is in two ways. So either as an action groupoid integrating the action Lie algebroid T star G, or as a group scheme integrating the bundle of Lie algebras T star G. And for the rest of the talk, it will be the second perspective.
Yeah, there's a good comment in chat by Dima that probably it's just a double groupoid, and I guess one of the groupoid structures you will lose in what follows.
Mm-hmm. Okay. So
Anna, can I sorry, because your original sigma was defined as using the Coxeter element, and everything here seems to be, again, like canonical. Once you have chosen that Coxeter element a representative, then you have the sigma, and then you just do this very canonical operation. And so the final Z can be expressed in terms of, does this have to do with some double Broussard related to C? Or
so are you
or maybe reduced?
So are you asking, can I give a kind of canonical construction of this that doesn't involve the choice of the Coxeter element?
Or can you the Z right, this Z, okay, is it possible to write the Z in, is it easy to write Z, express Z in terms of that Coxeter element?
That's I'm not sure. Probably there is an answer, but I'm not sure.
Okay.
Thank you. Another thing that I should say is that it is possible also to write Z in a way that doesn't really involve this choice, because what the Steinberg cross section is really a section to the adjoint quotient of the tilde. So if I everywhere that I have a sigma, I instead put like a T tilde mod W, then I would be rid of the choice, and it would be possible to write everything in this way. But then it would be hard to do this to study the Poisson and quasi-Poisson structures.
Okay, thank you.
Okay, so yes, so let me just recall where we are in the talk. So I've explained where the symplectic structure on Z comes from. And then I said that the rest of the plan was to compactify the fibers of Z, and then to see what happens to the symplectic structure on the boundary. And the place where the fibers of Z will be compactified is called the wonderful compactification of the adjoint group G. So I'll quickly give a kind of reminder of what this wonderful compactification is. So I pick a regular irreducible representation of G tilde. By regular, I mean that if you remember, irreducible representations of G tilde are indexed by highest weights. And the highest weight of this one is supposed to live in the interior of the dominant Weil chamber. So if you're imagining the picture for SL3, the Weil chambers look like this kind of fan. And my representation should live in this red cone, but it shouldn't live on any of the walls. And if I do this, I have the following diagram. So the representation map gives me a map from G tilde into non-zero endomorphisms of V. And then on the right, I can quotient by scalars. And on the left, I can quotient by the center. And if I do this, because G is of adjoint type, and because the representation is regular, the representation map on the top descends to an embedding of G into this projectivized endomorphism space. And the wonderful compactification is just the closure of the image of this embedding. So, this compactification has many very nice properties. It's smooth and obviously projective. And the action of G on itself by left and right multiplication extends to the boundary of G bar. So it's a G cross G variety. And this construction that I've given is completely independent of the irreducible representation B. So I will say a couple of nice structural features of the boundary, which hopefully I'll have time to use later. And then I will give at least one example. So the boundary of this compactification is a normal crossing divisor where each irreducible component is smooth. And the group orbits on this divisor are indexed by subsets of the integers 1 through L, which you can think of as subsets of the simple roots, in the sense that the closure of the orbit indexed by J is the corresponding partial intersection of divisor components. So in particular, this already tells us a couple of things. It tells us that orbit closures in the wonderful compactification are smooth because these divisor components intersect transversely. And it tells us that there's a unique closed orbit of minimal dimension, which corresponds to intersecting all of the divisor components. And these orbit closures have a very nice geometry. So to any subset J of simple roots, I can associate some data. I have a positive parabolic subgroup and a negative parabolic subgroup and their intersection. So if you're thinking about SLN, you can think that the positive parabolic looks like a block upper triangular matrix. And the negative parabolic looks like its reflection across the diagonal. So let me make sure that I draw it correctly. And then their intersection is just the block diagonal matrices in the middle. And then the statement is that every G cross G orbit indexed by J fibers over the product G mod Pj cross G mod Pj minus, it's the product of partial flag varieties. And the fiber is exactly the quotient of this Levy subgroup by its center. So if you notice, this is now a semi-simple group of adjoint type because I quotiented the center away. And when I take the closure of this orbit, then this fiber becomes the wonderful compactification of the smaller group. And in particular, from this picture, we can see that the unique closed orbit of minimal dimension, which I mentioned above, which corresponds to intersecting all divisor components, this is what I get when my parabolics Pj and Pj minus are minimal, which means that they are Borels. So this just looks like a product of two copies of the flag variety of the group G. Okay, so example, when G is PGL2, a simply connected cover is SL2. And here, every non-zero representation is regular. So I take the simplest one, which is just a standard representation, C squared. And this corresponds to just the usual realization of PGL2 as projectivized 2x2 matrices with non-vanishing determinant. And then the closure of this image of rho is the entire space of projectivized 2x2 matrices, which is just a three-dimensional projective space. And if we look at the boundary divisor consists of matrices with determinant 0. And via the Segre embedding, we can see that this is just a product of two P1s. And P1 is exactly the flag variety of SL2. So this fits into the picture on the previous slide. And now the boundary just has a single irreducible component, which is P1 cross P1. Okay, and then I also have a non-example to say that this doesn't generalize to PGLN for larger values of n, because in this case, the standard representation is not a regular representation anymore. It's one of the representations that generate the dominant Weil cone. So it sits on the edge. And so the wonderful compactification of G is not just an n² - 1 dimensional projective space, it's something more complicated. And in fact, you can see that for n strictly greater than 2, the compactification that you would get from the standard representation doesn't fit sort of wonderful properties that I said on the previous slide, because the boundary divisor in this case is just the vanishing locus of the determinant, which is irreducible, but it does get singularities where your matrices drop rank. So it's no longer smooth. Okay, so let me say also that the wonderful compactification comes equipped with what is called the logarithmic cotangent bundle. This is the bundle whose sections are logarithmic differential forms that have poles along the boundary divisor. So this is a sheaf of logarithmic differential forms, and because the boundary divisor is simple normal crossings, the sheaf is locally free, so it corresponds to a vector bundle. And this is what the log cotangent bundle is. And this log cotangent bundle has a canonical log symplectic structure that is totally analogous to the canonical symplectic structure on the usual cotangent bundle. And by log symplectic, I mean that if I take the top wedge power of the Poisson bivector, it's going to vanish with multiplicity 1 along the open part of each divisor component, and then with minimal multiplicity along their intersections. And in particular, I have an open dense symplectic leaf, which is just the usual cotangent bundle of G sitting inside G bar. So the wonderful compactification has a very nice feature, which is that its log cotangent bundle sits as a subbundle inside this trivial Lie algebra bundle on G bar. And I'll quickly explain how this works because it will motivate what we do next. So inside the log cotangent bundle, I have its pullback to G, which is just the usual cotangent bundle on G. And you remember that I can always identify this with the group G across the Lie algebra by trivializing and using the killing form. And then in here, I take an element A comma X, and I map it, let's see, to the point A, and then A applied to X, and then minus X. So this is a way to embed this, this cotangent bundle into this trivial bundle over G bar. In fact, you'll notice that this is an embedding using the usual moment map on the cotangent bundle of G. And so here I have, oops, this is an open embedding of T star G into the log cotangent bundle. And then the statement is just that the log cotangent bundle is isomorphic to the closure of this embedding over here. So this is now a closed embedding. So in this way, the log cotangent bundle becomes a bundle of Lie algebras over G bar, which extends the bundle of Lie algebras over G given by the log cotangent bundle G cross Lie algebra. Except that that this is a trivial bundle of Lie algebras, and this is not even locally trivial in the sense that when I go to the boundary, the Lie algebra structure on the fibers jumps. So
are those Lie algebras Lagrangian?
Yes. Yes. So this is, I didn't say this in this talk, but this is exactly if I use the realization G bar inside the variety of Lagrangian subalgebras, which is inside this Grassmannian, then this is just the restriction of the tautological bundle on the Grassmannian to G bar.
Oh. Okay, thank you.
So I was going to say, in terms of this data, what the symplectic leaves on the log cotangent bundle are, but I'm afraid that I won't have time, so I'm going to skip this part because it's not really essential to what we do next. But I will say, I will try to say a little bit. So I can characterize the symplectic leaves of the log cotangent bundle in terms of the sort of rep theoretic data attached to the group G in the following way. I pull back the log cotangent bundle to the orbit indexed by the set J. And then it's a fact that there's a base point in every orbit so that the fiber above that point looks like this product of parabolics with the same Levy component. So this is exactly the Lagrangian subalgebra that Lou just asked about. And then using the fact that everything is G equivariant, it's quite easy to see that the restriction of the log cotangent bundle to this orbit looks like a vector bundle over the orbit OJ. And the fiber of the vector bundle is just looks like this Lagrangian subalgebra. And then, in fact, the symplectic leaves that are contained in this pullback to OJ are just the fibers of the natural projection map where I take a point in this bundle and I project the first component in the fiber to the quotient of the parabolic modulo its derived subalgebra, which is just an affine space of dimension the cardinality of J. And I just want to make a remark that I've given this characterization of the symplectic leaves and it looks kind of not symmetric because why do I use only X and I don't care about Y? And the answer to this is that because this is the Lie algebra that can, maybe I won't write it for time, that because points in this Lie algebra consist of pairs with the same Levy component, then it doesn't really matter if I use X or Y, I will get the same leaves either way. Okay, so now the goal, like I said, is to compactify the fibers of the universal centralizer, which I think of as this family of centralizers living on top of the Steinberg slice sigma. And by compactify, I mean, I'm sorry, just all my slides seem to have disappeared. It's just a technical trouble.
Would you like to try to restart your notes?
This happened once yesterday, and I managed to make it go away. So, okay. Yes, so now we're back. Yes, so I was saying that the goal is to compactify these centralizer fibers. And what I mean by this is that sort of naively, I want to take every centralizer fiber and take its closure in the wonderful compactification and get something nice. And I want this compactification to be somehow compatible with the Poisson and quasi-Poisson structures that are around in this picture. So let me remind you of what the picture we've built so far looks like. So I had this universal centralizer, which was symplectic. And it was sitting inside this double, which was non-degenerate and in the sense of quasi-Poisson. And this double was supposed to be a multiplicative analog of the cotangent bundle, which of course is symplectic. And then when we were looking at the G-bar picture, we saw that the cotangent bundle has this kind of natural enlargement to the log cotangent bundle, which is log symplectic. So, so now the first question is, what goes in here? So where does the compactified universal centralizer live? And then the next question is, what happens to the Poisson structures along the boundary? And so first I will say what replaces the question marks. And in order to do this, I want to play basically exactly the same game that I was playing when I realized the log cotangent bundle of G bar as a bundle of Lie algebras. So I take my double DG, which again is just the product of the adjoint group and the simply connected group, and I embed it into the trivial G tilde cross G tilde bundle on the wonderful compactification using the moment map. And then the theorem or proposition, I guess, is that the closure of the image of this embedding is smooth, and it sits as a subbundle in the multiplicative version of the diagram that we had before. And the quasi-Poisson structure on the double DG extends to the boundary of DG bar. So I'll say very explicitly what this thing which I've been calling the logarithmic double actually looks like. Again, when we ask what the fibers are, we're really like looking at its pullback to every G cross G orbit in the boundary of the wonderful compactification. And the statement is that the fiber over this distinguished base point of the orbit indexed by J is exactly the sort of product of parabolic subgroups over the levy that integrates the fiber of the log cotangent bundle. So if we think of the log cotangent bundle as a bundle of Lie algebras, then this logarithmic double is exactly the bundle of Lie groups that integrates it. Except again, it's not a locally trivial bundle of Lie groups because the Lie groups that are sitting on the boundary are topologically different from the copies of G that are sitting in the open dense piece. And then there's an analogous statement for the quasi-Hamiltonian leaves, which are just parametrized, in this case by tori, by taking this canonical quotient. So now this is a product of copies of C star, and there are as many as the cardinality of the set J. Okay, so now we want to construct this partial compactification of the universal centralizer using the theorem from the beginning of the talk about preimages of Steinberg slices. So the picture is basically the same. I'll remind you that our double DG, which is just G cross G tilde, has a moment map, which takes a pair AH to conjugation by A in the first component and just inversion in the second. And this moment map is kind of compactified by the picture on the previous slide to a moment map for the quasi-Poisson manifold dg bar. And the image of the moment map mu was just pairs G and H, so that G was conjugate to H inverse. And the image of mu bar is going to be the closure of this variety inside G tilde cross G tilde. So I've written here this notation. And I'll say what it means. It means pairs G and H with the property that G and H inverse are in the, maybe I should say, in the closure of the same conjugacy class. So once again, using this transversality property of the Steinberg cross-section, which says that it intersects every regular conjugacy class in a single point, we see that, that a point in sigma cross sigma inverted intersects this image if and only if it's an anti-diagonal point. So again, if and only if it lives in the locus of points of the form H comma H inverse. And then the theorem from earlier tells us that the preimage of this anti-diagonal is a smooth submanifold of the logarithmic double, and it has an induced Poisson structure. And by working a little bit more, we can see that the fibers of mu bar above the slice are exactly the compactified centralizers that we were hoping for. And that the Poisson structure that we get on the compactified universal centralizer is log symplectic. And its open-dense symplectic leaf is exactly the universal centralizer we started with. So I think I will stop here, and thank you.
Okay. Well, thank you. Any questions?
One silly question. So the partly compactified centralizer is no longer a group scheme, is it?
No. So this is why this is why I said at the beginning that the way of viewing these things as symplectic groupoids it is no longer possible in the compactification.
Mm-hmm.
Is there like some interesting integrable systems, like maybe even on Z, like some Toda stuff?
Yes. So Z is there's this thing called the relativistic Toda system. And
sorry, what is it? Relativistic
Toda. So there are many Toda systems.
Yeah.
They're all named by physicists. So I don't know why their names are what they are. So this is relativistic Toda.
Relativistic.
So the if I took the universal centralizer, but I just took both components to be in the simply connected cover of G. So I forgot about the then that is called the completed phase space of the relativistic Toda system. And what this means for us, basically, for this universal centralizer and also for its partial compactification is that I think of Z bar as living above my slice sigma, and sigma is isomorphic to the adjoint quotient of the simply connected group G. So G tilde double bar G tilde. And here I have functions which are invariant polynomials on G tilde. And this is this is a polynomial algebra with rank many generators. This is the theorem. And these generators give an integrable system on Z bar, in the sense that when I pull them back, they Poisson commute. And this is what people mean when they say relativistic tota up to some kind of
Do you get any bi-Hamiltonian structures that are nonlinear? Like polynomial quadratic or cubic or whatever, in this way?
I'm not sure, but I've never
That
asked.
would be very interesting.
I don't know.
Okay, thanks.
How explicitly do you know this? So you say the symplectic form has those log singularities, right? So how explicitly do you know on different components of the boundary divisor those log singularities? Kind of, what is the control of the two form?
I'm not sure what kind of description.
No, but for instance, you probably have some defining functions for different components, right, of the divisor, and then the two form is probably d log of right of the near say di. It is d log of the function which defines di which something plus something smooth. So what do we know about this?
Okay, so I can say what I know. So
Maybe just to rephrase, how constructive, right? Of course, you're here formulating this theorem that it is log symplectic, and from that we know it's log symplectic, but nothing else. But probably in the proof, I suspect you probably have more information. So what's the information you have?
So I can say several things. The first thing that I will say is that on the double and the logarithmic double, it's possible to write down the two form, the quasi-Hamiltonian two form on DG, which is going to extend to some kind of like log quasi-Hamiltonian two form on DG bar in very explicit ways, using like the Hamiltonian vector fields for the group action, and in the same way that is normally done. So you can write in coordinates on the boundary of G bar, you can write explicitly what the vector field is in terms of the group action. In terms of coordinates on this universal centralizer, it's a bit more complicated to put kind of canonical coordinates on this, the way that we put canonical coordinates on the wonderful compactification. But it is possible to say in a totally explicit way, like what are the symplectic leaves along each stratum and what they're indexed by, and how they vary in families. And in fact, this is the next slide, which I didn't have time for, but it's a totally explicit description.
Thank you. Maybe another related question. So is it already on the archive, or?
Yes, it's already on the archive, and it has the same title as the title of this talk.
Okay, thank you.
So perhaps a related question to what Anton was asking. So these relative compactification being a symplectic, it has itself a symplectic groupoid. You know if it has a nice representation theoretical expression, the symplectic groupoid?
I don't know. I think to understand this, you would. So there's sort of a more basic version of this question, which is there is also a compactified universal centralizer in the additive case, so using the Lie algebra instead of the group. And that one comes straight from the log cotangent bundle of G bar. So I guess if I were trying to answer your question, I would first be asking myself, what is the symplectic groupoid of the log cotangent bundle of G bar? And I don't know the answer to this question. But I also think that it's probably potentially a nice answer.
But you do know the symplectic. You said that the next slide was giving you a description of the symplectic leaves. So
yes,
so
but I don't.
it should be related to that too.
Yes, but it's not obvious to me what groupoid they would come from.
Okay, so
I have a question. Sorry.
yeah, go
Sorry.
ahead, please. Yeah,
I,
go ahead.
Hello.
So I wanted to ask you about something that was asked earlier. It's about if you think of in this analogy that you have where the Lie algebra is replaced by G tilde, is it more than an analogy in the sense that you have an algebroid which is a bundle of Lie algebras that integrates to these bundles of Lie groups?
So
the question is if the geometry, the relevant geometry, it's also in sense compatible in the sense of groupoids, and it also comes from the infinitesimal version.
So I've been wondering this question kind of casually for a long time. The question of whether if I have a Lie algebroid with a Poisson structure, and it integrates to a Lie groupoid, can I somehow integrate the Poisson structure to something quasi-Poisson? Is this what you're asking, Ale?
Yeah, along those lines, or maybe Dirac, if it was the case.
Yeah. I don't know the answer to this question, but it's sort of, the question really presents itself in this project because there are at least 3 Lie algebroids with Poisson structures that integrate to Lie groupoids with quasi-Poisson structures. There's the group, and then there's the double, and then there's this logarithmic double. But I don't know. I think this is a very interesting question, and I would be very interested to talk about it, but I don't know what the answer is.
And another question is, these quasi-Hamiltonian, the group valued moment maps can be seen more generally in terms of Dirac morphisms. And I was wondering if you happen to have one of these generalized moment maps, what kind of slice on the target would allow you to do what you did with this particular slice?
So you would need, if we go back just to illustrate to where this theorem was. Okay. Right. So you would need you would need some kind of transversality condition to be able to pull back the Dirac structure. You would need some kind of like non-degeneracy of your intersection of your kind of pre-image manifold with the pre-symplectic leaves of the Dirac structure upstairs. And you would need a vanishing of the background 3 form. And then I think all of this is totally general.
I see. Okay, thank you.
Okay, maybe one more question? Any more questions?
Yes.
Yeah.
Anna,
Sam,
in
Hi, Sam.
your, hey Lou, hi Anna. In your Lie algebra version of this paper, you describe the compactification, the partial compactification in terms of Riesz algebra from a Coulomb branch. Can you do anything like this in the group case?
So it's sort of. So you can only do it when the group is simply laced. So when G is simply laced, then there's this theorem of Professor Kovnikov, Finkelberg, Merkovich that says that this groupy universal centralizer is the spec of equivariant K theory of the affine Grassmannian of G check.
Mhm.
And now this guy has a filtration by the weight lattice of the group G that comes just from filtration in K theory from like the paving of the affine Grassmannian. And if I take like the Riesz algebra of this ring, I guess, and then take a proj, then I will get exactly the partial compactification. Is this a satisfactory answer?
Yeah, that's what I was imagining. Sounds good.
Okay, so maybe we should stop here. It's already 12:30.
But Eckhart maybe.
Oh, sorry, there's another more question. Sorry, yeah, go ahead.
Maybe one quick question.
Yeah.
I was wondering if it's possible to bring automorphisms of the group into the story. I mean, there's also mild generalization of these group value moment maps where you look at twisted conjugation, twisted relative to some automorphism of the group. And so I'm wondering if for example, is there some analog of the Steinberg slice if instead of conjugation, you look at twisted conjugation?
I've never thought about this, but I would be very interested to know. I would be grateful if you would send me a reference, and I will think about it.
Okay, thanks. Sorry.
Okay, so maybe shall we thank Anna for this very nice talk. Okay. All right, so this will finish today's talk. Thanks to everybody for coming. All right, so see you next week. Yeah.
Thanks, Anna. Thanks, Lou.
Yeah. Bye-bye.